Doug, you left us on a loose end. We were trying to figure out where we were going with this.
Did you solve it while I was gone?
No.
I do not understand why my computer, how this always misbehaves, but I finally had to just give up and, you know, power or shut down or whatever you call it, and just turn my computer off, turn it back on. So
That's fun.
okay, where was we? Okay, here's where it gets awesome. So I'm sitting here with this and I'm thinking, does that look anything like, you know, what's in that table? Well, it will after we make this move.
Ooh, Landon, you were right.
What was Landon's idea?
I think it was to manipulate it into something that looks like it's in the table.
That's exactly right. We got to manipulate this so that it looks like something that's in the table. And this is what a big chunk of the chapters are about, is like, how do I do that? Well, let's just jump into it. Like, does it make sense that this is a fraction? This could be a fraction that if I unadded it, let me give you an example of this really quick. Like, let's say I was sitting here with like 3/10. Does it make sense because 10 is a composite number? That could be the answer to a fraction problem where you added halves and fifths. Does it make sense? 10 is composite. So like, let's unadd the fractions. Let's decompose it. In other words, this could be like 1/5 plus 1/2, or maybe it's 2/5 plus 1/2, or maybe it's 2/5 minus 1/2, or something like that. Does that make sense? Like, that's maybe possible. Well, that's kind of what's going to happen here. So the question is, is there some number for A and B that would actually cause those two things to be equal? Do you understand why I chose that? Well, think about our sheet. Take a look at, well, E. Notice how it's S minus something, like S minus 5 or S minus 2. And isn't that what I have? Like, I have S minus 5 and S minus 2. So it's like kind of looking close to that. If I could split that up into two parts, it would look like E. Then our Y equation would be E, wouldn't it? And of course, don't we already know the answer to this question? That's exactly what's going to happen. So, okay, if I was going to add these fractions together, don't you have to find a common denominator? So it'd have to be A times S minus A times 5 over S minus 2 times S minus 5. In other words, I'd multiply the top and the bottom of this fraction by S minus 5. Isn't that how you add fractions? And then do the same thing with B, multiply the top and the bottom by S minus 2. So that would be BS. That's convenient. And then I would have a common denominator, wouldn't I? So the question is then, if I add these, then can I get them equal to that red fraction? Well, notice I have AS plus BS minus 5A minus 2B all over this denominator that I just discovered, because now I can add those together. And the question is, is that possible for it to be equal to this? Is there some values for A and B that would make that equal? Well, in order for that to work, hence, wouldn't A plus B have to be 3? Isn't that what this tells us? AS plus BS, those are the S terms, and I have to get 3S, so wouldn't A plus B have to be 3? So again, at this point, it could be like, oh, 2 and 1, or 3 and 0, or 10 and -7, like there's all kinds of choices. But then I have a second one. In order to get 21, my constants, -5A, -5A, and -2B, those are going to have to take care of the constant, which is supposed to be -21. So 2 equations, 2 unknowns. There's going to be an answer to this. So there is an A and a B. I am going to be able to split this up. And so let's see, I can do this in my head, right? This isn't that hard. I'm not going to cheat. If I multiplied this one by 2, then when I have 2b and negative 2b, and I could add. So I have 2a and negative 5a, that'd be negative 3a. 2b and negative 2b, that'd be 0b's. So those are gone. And then 6 and negative 21 is negative 15. And so a would be 5. Came out easy. Came out nice. Well, if I put a as 5 back into this equation, doesn't that mean b has to be negative 2? Now, just to make sure I didn't screw up, I want to stare at this equation to make sure that if I use those values for a and b, do I get negative 21? So negative 5 and 5 is negative 25. Minus 2 times minus 2 is 4. Negative 25 plus 4, yeah, that is negative 21. So I actually got it.
That's what we have in the denominator too. Oh wait, almost.
Yeah, it's similar.
Is that coincidence or is that important?
It's a coincidence. That happened because back up here, when I was trying to find numbers really quickly for C1 and C2 that made this equal to 0.
Oh, I see.
I just thought, well, this is a 5 and this is a 2. So if I made C2 a 5 and C1 a 2, then they'd both be 10. So that's kind of a coincidence. It won't always be the case. So then let's see, where are we now? Can't I then say that my Laplace transform of this y that I'm trying to find is now equal to, well, a over s minus 2, 5 over s minus 2, and then plus b, but b was negative 2 over s minus 5. Do you see that that's progress? Why is it progress? Because it's starting, and we don't mind the plus signs, but it's starting to look really close to this now. Do you agree with that? Except for there's a 1 on top. Notice it says there's a 1, not whatever you want. It doesn't say b, like that can be anything you want it to be. It's got to be a 1. But isn't this exactly what we have on the bottom now? We have s minus 2 and s minus 5, but we don't have a 1 on top. And how do we get a 1 on top?
Just pull it out. Just factor it out.
Just pull it out. In other words, 5 times 1 over s minus 2 minus 2 times 1 over s minus 5. And so isn't this, switch colors, isn't that just 5 times the Laplace transform of e to the 2t, according to the chart? If that's 1 over s minus 2, isn't that what you get if you take the Laplace transform of e to the 2t? Isn't that what we say? Again, let's look at this sheet. Get rid of this junk. Laplace transform of e to the 2t is 1 over s minus 2. Isn't that right? And isn't this second one minus 2 times the Laplace transform of e to the 5t? And so if that's equal to the Laplace transform of y, then doesn't that mean then if I sort of get rid of the Laplace transforms, remember how I took the Laplace transform of both sides and everything was Laplace transformed? Well, isn't that what I have now? Like Laplace transform, Laplace transform of junk equals Laplace transform of junk minus Laplace transform of junk. Like, can I do the opposite? Like, to start this process, I took the Laplace transform of both sides. And so now couldn't I take the inverse Laplace transform of both sides? So I get my y back on the left side, and I get 5e to the 2t for that one, and I get minus 2e to the 5t for this one. Isn't that what we got by guessing up here? So that's kind of cool in that we didn't have to guess. However, was it less work Not really.
So I've got a question here in terms of like the best way to do this. Instead of plugging in values now, couldn't we also just leave the y of 0 and the y prime of 0 in there?
Absolutely. Yep. In other words, if we said y of 0 is c1 and y prime of 0 is c2, in other words, we haven't decided. I don't know what they are yet. I don't know. I don't know what the initial starting amount is. I want to have a model for all tanks with liquid flowing in. I don't know how much was in there at the start, and I don't know what the rate of change was at the start. Yeah, you could do that. It would make the algebra a little uglier, which is why I didn't do it to start with. So
you were nice and chose one with distinct roots. I feel like complex roots with Laplace transforming, that would be bad.
yeah, so how are we supposed to recognize it with complex roots and so forth? And the beautiful part of this is that's what's kind of cool is you're basically going to start saying, hey, this looks like, what I have on that right side, it looks like, this. Or then you might say, well, no, in this problem, it doesn't look like that. It looks like this. And remember, aren't these the kind of answers we got for complex roots? So it'll be like, no, the right side doesn't look quite like that. It looks like something else. And so you can see why what happens in this class, or what makes it hard, and why books have 2 more sections before they show you what I just showed you, is because how do you get what results from all of this, which was, where did it go? Here. How do you get that, or more specifically this? How do you decompose that to look like something that you built in that chart? That's an art. That's a bit of an art. It takes a little bit of time.
Yeah, I kind of want to say it's easier to just leave it in y of 0 and y prime, because then certain sections of this, before you plug in numbers, become really friendly to work with, because like the y prime section is just, the denominator would just be, oh shoot, never mind, that is not that easy. Okay, never mind.
It is a little bit painful. Yeah. I mean, we're sort of done now, but let me just, I'll erase this. But what if that wasn't a 10, but that was an 11? How would that have changed this problem? Well, yeah. Notice it, and now it doesn't factor, right? And so it still has answers, but now they're decimals. You know what I mean? It's like it actually does still factor. You were never taught it this way. It still factors. It just doesn't factor to s minus 2, s minus 5. It factors to something like s minus 1.932645 times s minus 5.1629487, which are still real roots that come from the quadratic formula, but they're just kind of decimals. And so, or what if when we tried to mess with s squared minus 7s plus 11, what if it was a complex answer? Like, how are we supposed to notice that? Or how's that happen? How does that work out? And so the idea that, yeah, I get messes. I'm going to get a mess on this side after taking the Laplace transform on both sides and finally solving for Laplace transform of y. I'm going to get a mess on the right-hand side. And it's going to take a lot of practice to learn how to decompose that. Now, the funny thing is that takes enough practice that in the beginning, it's going to kind of feel like guessing to you. It's like, we're back to guessing again. Like, I don't know exactly I'm not sure how to get that to look like it's supposed to look. And notice the one I just did was quite a bit of trouble. And yet, wasn't that the easiest question on the last test? I don't even know where it started. Wasn't that the easiest question on the last test because it had distinct roots and because it was equal to 0? No trick questions, right? Nothing weird. Not a complex answer, not a repeated root and so forth, and equal to 0 on top of all of that. So it just kind of feels like what we ended up with here that we needed to decompose, that's the simplest possible decomposition there is. And yet, I mean, that wasn't terrible. But it wasn't easy either. So the question, so the practice, the thing we got to practice, because you actually now know the concept. There's nothing else that I need to teach you about this section other than how do we deal with that mess? How do we get better at the algebra that's required to decompose that into something that I can recognize on this sheet? So we will be, and we don't need to make any more of these, but we just need to be kind of familiar with what I see over here. So the, you know, notice this one, for instance, this one has a constant on top, just a constant. That's when you get sine. But when you get cosine, it has not only a constant, but also an S up there. So, you know, what does that look like? What else do we have over here? Well, notice that's just an S squared. So if it wasn't S squared, remember how we had a second ago, we had like S squared minus 7S plus 10 or something like that. Well, what if there was just an S squared? Well, that'd be a lot better, because then it would be T. So we're just trying to look for, you know, what can we do to get it to look as simple as possible. And you remember E came up a lot. Like this is one of the ones we're going to see more than any of the rest of them. That's the E one is one that's going to come up a lot. But that's an interesting one. Do you notice what happened there? Like a second ago, didn't we have, oh my gosh, it just went dark again. Didn't we have, what was it, S squared minus 7S plus 10? Well, notice this question is more like, you know, what if the middle term was missing and it was just S squared plus 10? And of course, it'd be easier if that wasn't a 10, but it was a 16, because then couldn't you say that's S squared plus 4 squared? And you'd be like, oh, it looks like that. Oh, it's a sine. Like now all of a sudden the answer is sine. Isn't that weird? Like we just got E a minute ago, and yet all we have to do is have the middle term missing, and then suddenly it's a sine instead of an E. I mean, isn't that kind of cool? So we just have to get kind of good at, first of all, recognizing what we're trying to get it to look like, and then what algebra and manipulations do we have to do to get it to look that way. Let's see. Okay, I think we should stop there. I'm realizing I didn't show you this yet, but I can't remember. Let's wait till we need to know that before I teach it to you. So right now that one's kind of weird, but we've touched most of what's on the sheet now, at least my cheat sheet, which actually limits it just to the things that you really need to understand. These are unusual extras that are hyperbolic, sine and cosine. Those are just kind of cool. I only point them out here because they look so similar to the cosine ones up here. Like it almost looks the same. And so, and you're probably not familiar with what hyperbolic sine even is. Although you will be at one more awesome project, and you're gonna.
Oh, cinch! Oh boy.
Yeah, we're gonna look at the St. Louis arch, which is a catenary curve, and how its equation is found thanks to second order differential equations. So you're going to learn what hyperbolic sine and cosine are. But you've touched everything on this page now, except for this cool dodge right here. In other words, you should be familiar with these. So have I posted this for you? Do you guys have this sheet now?
I don't think so, no.
Okay, I'll make sure that I'll probably put it in my open math instead of in today's notes. I'll probably put it both places.
That's going to be like a test handout thing too, right?
Exactly, yeah.
Pretty cool.
Because we're not making this anymore. We're using it from now on. We're not ever making these.
Sweet.
So have a sense of familiarity with it, and then you're on your way. And by the way, before we go out the door, do you recognize this one based on what I taught you today? What did we say was cool whenever it was the Laplace transform and it had an E in it?
The S grows a minus A, I think.
Yeah, S turns into S minus A. In other words, I'll show you this up above in a second, but if it was the Laplace transform of t to any power, t to the third, t to the fourth, whatever, up above, it says that's n factorial over, you may remember, s to, well, one more power than that. If that was t to the third, then this would be s to the fourth, one more power than that. And so what happens if you throw e to the AT in there? Well, all it does is replace that s with s minus a. Isn't that what we learned today? So we didn't touch that one. I haven't like physically shown you that one, but there it is right there. So if I throw e to the a in there, then all you're really doing is replacing s with s minus a. Like, that's kind of cool. So if you just have s, then that means it was a t equation that it came from. Just t, like 4t, 5t, 5t squared, whatever. If you just have an s. But if there's an e in it, then you won't have s, you'll have s minus a, right? So begin to familiarize yourself with this sheet. But really what I want to do now, rather than, we're actually skipping 7.4, which in the book is where you practice. And I just think this doesn't do any good to practice when you don't understand why you're practicing it. You just practice decomposing stuff like that, because that's what we got to get good at. We get a big mess on the other side, and we've got to somehow, split it up into pieces until it looks like a bunch of Laplace transforms that we recognize. But what I don't want to do is just give these to you and say decompose them, because in the book hasn't even shown you that you can even do anything with this. What I want to do is build these every time from now on. We actually have 3 days next week where we're talking about 7.5, and it's really a combination of 7.4 and 7.5, where I'm just going to give you problems like we've been doing, just like your test. It's like we could take all the test questions and then see if we can do them with a Laplace transform. That's really what it comes down to. So we're going to take the time to build this mess. I'm not just going to hand it to you. We're going to make it, and then we're going to like figure out how to decompose it. And you'll get better at that. You'll get to where you're like, okay, I can do that now. Okay. It is late.
Thank you, Doug.
Good to see you all again. And as always, stay after if you have.
Thanks, Doug. See you next week.
See you, Doug.
Later.
So you mentioned those test questions. I could work through them and just submit them to you later.
Mm-hmm.
I got 2 of them done. I think I only had 1 more, so I'll get that turned in tonight, and then you can just hang on to them in case I end up with a close grade.
Yep.
All right. Have a good weekend, Doug.
You too. Thanks, Cheyenne.
Mhm.